Hi everyone, welcome to Unit 4, which is on chemical bonding. Today, in Lesson 1, we're going to talk about an introduction to chemical bonding. I'm going to go over some basic terms that I think are important, as well as teach you how to identify what type of bond we're going to be discussing. Okay, so let's take a look at our first question. It says, what is a chemical bond? So if you look, it says that a chemical bond is a mutual attraction between the nuclei and the valence electrons, which we've talked about for a long time now, of different atoms that binds them together. Now, at the bottom there, you see three different pictures. These three different pictures represent three types of chemical bonding that we're going to talk about. All the way on the left, you see an ionic bond. An ionic bond is where one electron is transferred from a metal atom to a non-metal atom, forming a positively charged metal ion and a negatively charged non-metal ion. The second example, which is in the middle, is an example of a covalent bond, and that example has a picture of water. So water has covalent bonds between the oxygen atom in the center and the hydrogen atoms that are kind of to the lower left and lower right of that oxygen atom. One of the things that we're going to be working through in this chapter in a few weeks is how to figure out what shape these different molecules take. And that's going to be very important in determining how they behave. Finally, the third picture all the way to the right is an example of metallic bonding. We're going to talk a little bit about metallic bonding today. In metallic bonding, you have positively charged metal ions, and then their electrons, which are delocalized. We'll talk about what that term means, but they're free to move from one atom to another. All right, let's take a look at metallic bonding in more depth. It says metallic bonding is chemical bonding that results from two or more atoms sharing valence electrons. And in this case, those valence electrons are free to move from one atom to another. This accounts for many of the properties that we observe with metallic bonding. So let's take a deeper look into what exactly a metallic bond is. So if you notice that picture at the bottom, I have the word sea in quotes. Sea, like an ocean of these mobile electrons. Electrons are able to move from one atom to another atom freely, which is kind of unique. We don't see that in covalent bonding. We don't see that in ionic bonding once the initial transfer of electrons has taken place. So metallic bonding is kind of unique. Properties that are characteristic of metallic bonding and are a result of these mobile electrons between metal ions are, number one, electrical and heat conductivity. One of the things that makes metals so useful is their ability to conduct electricity. So if you think about plugging in the wire to your computer, embedded underneath the insulation that's on the outside of your wire, you're probably going to find copper on the inside, and that copper wire allows for electrons to move. So the electrons moving allow our computer to take AC current that's available in our house and convert it to our DC power that our computers use. And heat conductivity. So we also use metal in cooking. And one of the things that metals are very efficient at doing is transmitting heat. So if you have, let's say, a gas burner, and you're generating a tremendous amount of heat energy, it's able to transfer that heat energy through the metal to your food in order to cook it. Second thing is that metals are malleable. That means they can be bent or shaped. So the ability of these electrons to move and act as a cushion between metal, positively charged metal ions, allows for this flexibility in the material. So malleability, or the ability to bend and shape something, is a property that is unique to metals because of that ability to cushion these metal ions with these mobile electrons. Third, and sort of related to malleability, is ductility, which again is similar to malleability, but in this case it's very specific, meaning that you're able to stretch out the metal into a thin wire. And we of course use that all the time in our wiring, both in our house and our computers. And finally, one of the characteristics that we're going to talk about today are variable melting points. So some melting points for metals are extremely high, and some metals have really low melting points. So if you think of something like mercury, that's a metal but its melting point is so low that mercury exists as a liquid at room temperature. There's another metal called gallium, which also has a relatively low melting point, so low that if you took a piece of gallium and put it in the palm of your hand, you could squeeze your hands together and liquefy that metal because its melting point is just above room temperature. All right, so now what we're going to do is try and make sense of why this happens, and we're going to do that by looking at the group 1 metal atoms. So I'm going to take a look at some melting points here. So lithium, we'll notice, melts at 181 degrees, sodium at 98, potassium at 63, and rubidium at 39. Now, one of the things that you're going to notice is that the melting points decrease as you go down a column or a group on the periodic table. So now, think back to the last chapter. What happens as we go down a group on the periodic table? The atoms get bigger. They get bigger because they have more energy levels. So, as the atoms get bigger, you would think that they're getting stronger, but actually they get weaker. So a low melting point means you can separate the atoms easily. A high melting point means it's difficult to separate those atoms. So as the atoms get larger, the energy required to separate them decreases. Does anyone know why? Well, it has to do with the fact that the electrons of one atom are being attracted by the nuclei of the other. So the further away that nuclei is from the electrons of a nearby atom, the weaker that attractive force is. So bigger atoms are going to have lower melting points. Smaller atoms are going to have higher melting points. So think about this in this way. If I have two different, and we'll use lithium as an example, two different lithium atoms. They each have one valence electron because they're in group 1. So we put those valence electrons in the middle. They almost act as a glue between the two lithium atoms. And because there's just one valence electron, it's like having one drop of glue on each of those. Now, let's take a look at a much larger atom, something like cesium. Well, if I look at cesium, the atom is going to be larger, but because it's in group 1, it's still going to have just one valence electron. So one valence electron means that we have the same amount of adhesive, the same amount of glue holding them together. Here's another way to think about it. Imagine having two ping pong balls, and you have 2 drops of super glue to try and hold them together. So 2 very light, very small balls, you're going to put 2 drops of glue on there. They're going to stick together really well with 2 drops of super glue. Now imagine that you're talking about a much larger atom, like cesium, but instead of using ping pong balls to represent it, we use bowling balls, much heavier, much bigger. But because they're also in group 1, they only have one valence electron. So the same 2 drops of glue that we use to hold together the ping pong balls, we would use to hold together the bowling balls. Well, you're going to find that it's going to be easier to separate the bowling balls from each other with those 2 drops of glue than it would be to separate the ping pong balls from each other with the same amount of adhesive. So what we can conclude is that as the size of an atom increases, the melting point and the boiling point, for that matter, are going to decrease. So let's take a closer look at melting point values. So on the screen, you'll see that I've listed the melting point values for group 1 metal atoms. So I have lithium going down to francium, and you notice a consistent decrease in melting point for the reasons that we just discussed. Now, how does that change when we look at group 2? Well, you'll notice I identified the melting points for calcium, strontium, and barium, and you notice the same trend. So going from calcium to a larger atom, strontium, to a larger atom, barium, you notice that the melting point decreases, just like you would expect. Larger size, melting point is going to be lower. However, notice the difference in melting points between the group 1 atoms and the group 2 atoms. The group 2 atoms have much higher melting points, even when the number of energy levels is the same. So for example, compare potassium, which is in the 4th period, With calcium, which is in the fourth period, potassium melts at 63 degrees Celsius, where calcium melts at 842 degrees Celsius. Why is it so much higher? Okay, let's take a look. So if we look at the two examples that I have on the screen right now, you're going to notice that the example on the left side, right here, represents a group 1 metal. And each of these electrons are like the glue holding it together. When we jump over to a group 2 metal, we have twice as much glue because group 2 metals have 2 valence electrons. So there's twice as much adhesive holding them together, even though they're relatively similar in size to the group 1s in the same period. So much more adhesive means harder to rip them apart, means much higher melting points. So we observe much higher melting points for group 2 elements compared to group 1 elements in the same period. So if we look and we compare potassium to calcium, we have 63 to 842, rubidium to strontium, and then finally cesium and barium. Okay, that wraps up everything that we're going to talk about in terms of metallic bonding. We looked at properties of metallic bonding, heat and electrical conductivity, malleability, ductility, and then we looked at the trends in melting points. So the larger the atoms get, the weaker those bonds are, the weaker those forces of attraction are, the lower their melting points and boiling points are. So at the top of a column, high melting points and boiling points. At the bottom of a column, where the atoms are much larger, low melting points and boiling points. When we compare two atoms in the same period, which is what we were doing on this slide, we find out that elements in group 2, because they have twice as many valence electrons, have much stronger bonds and therefore much higher melting points when compared to elements in group 1. Now we're going to move on and talk about ionic bonding. So in this case, we're answering the question, what is an ionic bond? Well, as it says on the slide, an ionic bond is chemical bonding that results from the electrical attraction between cations, or positively charged ions, and anions, which are the negatively charged ions. So how do we get these positive and negatively charged ions? Well, if you look, we have sodium and we have chlorine. Sodium is going to give up its one valence electron to chlorine. The result is a positively charged, because now protons outnumber electrons, a positively charged sodium ion, and chlorine, which gained that electron, is now a negatively charged chloride ion. The positive sodium ion and the negative chloride ion attract each other because of what's called an electrostatic force of attraction. Let's take a look at our next slide. In a covalent bond, so this is our third type of bonding, so we had metallic, we had ionic, and now we have covalent. In a covalent bond, we have something a little different. In a covalent bond, we have chemical bonding that results from two or more atoms sharing valence electrons. So in ionic bonds, electrons are transferred. They go from one atom to another, forming two ions. But in a covalent bond, they're not transferred. Instead, they're shared. The two atoms cooperate together to fill their outermost energy level with either 2 or 8 electrons. For the most part, it's going to be 8 because helium doesn't really bond. Okay, so in this picture, you can see that the purple circles are the electrons that hydrogen is bringing into the molecule, and the orange circles are the valence electrons that oxygen brings in. So oxygen, group 16, you remember from the last chapter, 6 valence electrons. Hydrogen, group 1, 1 valence electron. So the purple circles represent the hydrogen's electrons. Hydrogen is sharing its electron with oxygen. In fact, 2 different hydrogens are each sharing 1 electron with oxygen in order to get oxygen up to its required 8 electrons. Okay, so this page explores covalent bonds a little deeper. Now, it turns out that when you're sharing something, there are 2 different ways that you can share it. You can either share it equally, or you could share something unequally. So imagine you and your sibling are sharing a car. And on Mondays, Tuesdays, and Wednesdays, you can drive the car wherever you would like. But on Thursdays, Fridays, Saturdays, and Sundays, your sibling gets to take the car. So you get 3 days, they get 4 days. That's called unequal sharing. So someone has the car more than another. Or you could share a car equally. So you would have it on Monday, your sibling on Tuesday. Then on Wednesday, you get it back. Then on Thursday, they get it back. And you just keep swapping days all the way through. That's called equal sharing. So if you notice, a non-polar covalent bond is a covalent bond in which the bonding electrons are shared equally. So no pole, non-polar. No one has a stronger hold on those electrons. So a non-polar bond is where they're being shared equally. A polar bond, as you can read, it says a covalent bond in which the bonding atoms have an unequal attraction for shared electrons. That means one atom is pulling on those electrons harder than the other. So if you look at the picture on this page, it says on the left, we have an equal sharing. So 2 chlorine atoms are sharing electrons equally. They have the exact same electronegativity values, so they're pulling on those electrons perfectly equal to each other. In the middle example, you have a polar bond. You have hydrogen, which is slightly weaker than chlorine, which is slightly stronger, more electronegative. So you notice that the electrons are closer to the chlorine side than they are to the hydrogen side. And as a result, you get a partial negative, a partial buildup of electrons on the right side of this molecule as compared to the left. And then finally, if you imagine 2 people or 2 atoms sharing electrons, and one atom is substantially more electronegative than the other, they're not able to share nicely, they don't play nicely together. So in this example, we have chlorine, which is much more electronegative than sodium, rips the electron off of off of sodium, forming a chloride ion and a sodium, positively charged sodium ion. So equal sharing here on the left, unequal sharing on the right. And then to the far right, the sharing is so unequal that chlorine rips off the electron from sodium, steals it, keeps it for itself, forms a negatively charged ion, and consequently forming a positively charged sodium ion. So that begs the question, how do I know what type of bonding is taking place? Well, there are 2 ways that we're going to learn how to do this. The first is by identifying an atom as a metal or a nonmetal, and we'll practice that. The other way is to look at differences in their electronegativity values. So if their electronegativity difference is really small, that means they have almost the same electronegativity values, what we're going to find is that they are considered to be nonpolar covalent. This is pretty rare. Pretty much the only time that you see nonpolar covalent is like we saw in the example when you have 2 copies of the same element. The second possibility, if that electronegativity difference falls between 0.3 and 1.7, you have a shared bond. They're sharing those electrons, but they're sharing them unequally. This is very common. And any electronegativity difference that falls in that 0.3 to 1.7 threshold is going to result in a polar covalent bond. Finally, if you have a sharp electronegativity difference, meaning one is highly electronegative, the other atom is very low electronegativity, then you're going to result in an ionic bond where the highly electronegative element steals the electron from the low electronegative element, forming these positive and negative charges. So here are 3 examples. So when we go through these examples, what you're going to see is how we're going to calculate these electronegativity difference. So the bond between hydrogen and sulfur. If you notice, the bond between hydrogen and sulfur has electronegativity values of 2.1 and 2.5. That means the difference in electronegativity is 0.4. So you would subtract 2.5 minus 2.1, you would get 0.4. According to our graphic, 0.4 means that that is a polar covalent bond. So they're sharing electrons, but they're not sharing them equally. Okay, our second example is a bond between calcium and chlorine. Calcium, you can see its electronegativity value is 1. Chlorine has an electronegativity value of 3. So the difference in electronegativity values is pretty significant here, a difference of 2. So a difference of 2 in terms of electronegativity puts us firmly in that ionic category. So a bond between calcium and chlorine is going to be an ionic bond. And finally, our last example is between hydrogen and bromine. So if you notice, hydrogen is 2.1, bromine is 2.8. That difference is 0.7. That again puts us in the polar covalent bond category. So 0.7 difference here. The calcium and chlorine was a difference of 2, so that's over here in the ionic spot. And then hydrogen and sulfur was 0.4, so that was also a polar covalent bond. 2.5 minus 2.1 is 0.4, polar covalent. 3.0 minus 1.0 is 2.0, ionic. And then 2.8 minus 2.1 is 0.7, polar covalent. The last thing that I want to mention is that a bond between a metal and a nonmetal is going to be an ionic bond, even if the threshold is very close. So sometimes you see differences in electronegativity that fall right along the 1.3, or excuse me, 1.7, 1.6-ish range. And what you're going to do is you're going to say, nope, I know it's close to 1.7. It might not be over that threshold, but I have a metal bonding with a nonmetal, so I know that's going to be an ionic bond. So just keep that in mind. There are a few exceptions to those thresholds. Okay, at this point, I'm going to ask you to open up the identifying bond types assignment. I'm going to go through one example of each of those problems with you, and then after that, I'm going to ask you to finish that assignment for homework. Okay, so I've opened up the identifying bond types assignment, and the very first thing that I want to point out to you is there are two sides to this page, or 2 pages to this document. So in the first page, we're going to be using that last point that I just made. If we have a metal and a nonmetal, we're going to have an ionic bond. If we have 2 nonmetals, then we're going to have a covalent bond. And if we have a metal and a second metal, we're going to have a metallic bond. So let's take a look at all 3 of these examples. This periodic table is meant to help you identify whether something is a metal, if it's in that like blue-gray color. If it's a nonmetal, that's kind of the copper color or tan color, or a metalloid, which is in that green section. So let's take a look at our first example, which is sodium chloride. Again, I'm only going to do the first example with you. You're going to finish the rest of the assignment on your own. Sodium is over here. It's Na, so this is clearly a metal. So in this box, I'm going to type in metal. In the second box, we have chlorine. Chlorine is over here in the nonmetal portion. So in the second box, I'm going to type in nonmetal. And then finally, because I have a metal and a nonmetal, that's going to be an ionic bond. So in each of these, I would like you to type whether you have a metal or a nonmetal. And then finally, based on what you have, what that bond type would be. So just a real quick recap. Metal, nonmetal, that's ionic. Non-metal, nonmetal, that's covalent. And finally, metal, metal, that's metallic. We will not be able to decide whether the covalent is polar covalent or non-polar covalent by using this method. Okay, when we scroll to the second page, we're going to notice a second periodic table. This one gives us different information. So instead of telling us whether we have a metal or a nonmetal, we have electronegativity data. So if we look at our first example, which is the molecule sulfur dioxide, we're going to identify the electronegativity value for sulfur, which is over here at 2.5. We're going to identify the electronegativity value for oxygen, which is over here at 3.5. In this box, you can do the math. 3.5 minus 2.5 equals 1.0. And then going back to that chart that we just completed in our notes, a difference in electronegativity of 1.0 means that we have a polar covalent bond. So in this box, we're going to type in polar covalent. So please finish On the first page, numbers 2, 3, 4, and 5, and then on our second page, numbers 7, 8, 9, 10, and 11. Be careful, there is at least one instance where the electronegativity difference might trip you up, so just look out for that. If you have any questions, please consider stopping by office hours. Have a great week, everyone.